So welcome everybody. This is the Safe Reinforcement Learning Online seminar. Today we have as guest Professor Bodai. He is an assistant professor in Georgia Tech and a staff research scientist at Google DeepMind. He obtained his PhD from Georgia Tech, and his research interest lies in developing principled and practical machine learning methods for decision AI, including reinforcement learning. He is recipient of the Best Paper Award at ISTAS and NeurIPS workshops. He regularly serves as area chair on senior program committee member at all major AI and ML conferences such as ICML, NeurIPS, ISTATS, and ICLR. So welcome, Professor Dai, and you can start your talk when you feel the floor is yours. And if there is questions from the audience, please write in the chat or you can also ask in the end, and we can start now. Thank you.
Thanks, Joseph, to introduce me, and thanks for inviting me to give the talk here. Okay, I think we will directly dive to what I'm talking about today, which is the representation-based reinforcement learning. I'm Bodai, and this is a long-term joint work with many collaborators, including Tongzheng, Chenjun, Tianjun, Sherry, Lisa, Nali from Harvard, Dale, Chaba, and all the other collaborators all came from DeepMind. And yeah, let's start. Okay. Okay, I think this is outline of the talk today. Basically, we will talk to something which actually obvious in reinforcement, but not too many people talk about that, which is the difficulty of model-based and model-free reinforcement learning. Actually, that's the motivation why we want to go beyond, why we want to process kind of representation-based reinforcement learning besides the existing model-free and model-based reinforcement learning. And then we will start with concrete stochastic, actually classic stochastic nonlinear control to get some inspiration from there, which inspire us to provide a coherent solution with reinforcement learning with linear representation, especially use this kind of thing for MDP and POMDP. I think this is basically the whole outline of the talk. Okay, let's first give some definition. I think if you guys are all familiar with reinforcement, this is very standard. We most of the time we will talk about a Markov decision process as the model for the reinforcement learning. Usually we represent the model MDP as a tuple, which includes the state space action and reward function, which basically gives the state and action. You will have a scalar number. And another important thing is the transition operator, which is given your current state and action. The transition operator basically stands for conditional distribution, which generates the probability of the next step. Meanwhile, we also have the initial state distribution, which is saying your random start from somewhere over the all state. And we usually define value function, which denote as V. Essentially, that is the ready to go function in control community. Basically, it's expectation of the actually a cumulative expectation of the reward for the future. And also Q function, which is condition on current state and action for the future accumulated reward. And also we denote policy as pi, which is the conditional distribution, condition on current state, and you have the action distribution, so on and so forth. So basically these are all the vanilla definition. We don't have too much question, so I will skip further about the discussion here. And then as I mentioned, we will discuss a little bit about the current two major paradigm of reinforcement learning. One is called model-free reinforcement learning. Basically, model-free reinforcement learning is saying we don't fit the model, we directly fit the quantity, which will be used for my control. Specifically, for example, here, where we discuss the Q learning, and instead of fitting the model and apply the model-based control on the fitted model, we directly fit the Q function based on the Bellman recursion. And with that, we can the Q function, optimal Q function will induce a policy, for our control. Basically, the Q learning is derived based on the Bellman recursion, and which we end up like a temporal difference update. And we definitely can introduce neural network instead of the tabular Q function. We introduce neural network, and then update becomes, it's not gradient, but it's just derived from the TD update from the tabular to the parameter of the Q function neural network. And this is one category of the model frame. The other category is even more direct. We even don't utilize the recurrent structure in MDP. We directly aim at the maximize the policy. So that leads to the policy gradient. I think this is also well known in machine reinforcement community. We parameterize pi, and the accumulate the value of pi basically is as I listed here, accumulate for the future. And then we definitely can calculate the gradient with respect to the parameter of policy, which actually, as listed here, is tractable. And then we will use this to update policy and so on and so forth. And based on different kind of estimation of Q and the parameterization of policy, we will have a lot of variants like natural policy gradient and soft actor and so on and so forth. But all of this could be understood as a variant of the policy gradient. Okay, we introduced the two major class of the model free reinforcement learning. Actually, it is good in terms of modeling part, because it is easy to incorporate the function approximator and for example, deep neural network, and also we can do the end-to-end learning from based on the gradient to update the policy of Q function. But the drawback actually is also significant. First of all, if we utilize Q learning with deep learning, it's really difficult to calculate the uncertainty so that it's not easy for us to do exploration. Okay, I think that's one drawback. Another one actually is that if we introduce neural network, there's no way to guarantee how good or how bad the solution will get. Okay, this is we call planning. Okay, I think any questions so far? Yeah, if you have any question, just interrupt me. I cannot see the discussion. I mean the chat channel here. Okay, another category is called the model-based reinforcement. It's totally different from model-free. I think this is also well known. Instead of feeding the Q or feeding the policy directly, we first feed the model. And then based on model, we utilize some existing model-based control method to extract the policy from the fitted model, and then use the obtained policy to collect data and refine my model and so on and so forth. The philosophy actually is the basic algorithm framework is quite simple. It's just like such kind of stuff. And there are several kind of variant like LQR, which is widely applied in control. The only thing here is that instead of it's instantiate the model-based reinforcement learning with linear, dynamic, and the co-directed model. The benefit which induces this kind of optimization for control. The benefit of this is that we know this is convex optimization, so we can guarantee the planning error. That's first thing. And the second is that actually we can we have a very good uncertain estimation for this. So basically, it's good for us to do the exploration, as I mentioned here. But bad thing is it is linear, right? So which means we have very strong model assumption, and it's not easy to capture the real thing. So in that way put it, you pay a lot of effort to make this perfect, make LQR perfect in practice, but it's still far away from the optimal policy because you add so strong constraint on the modeling part. Another one actually is on the other side of the, actually it's totally opposite to the linear quadratic regulator, which is deep model-based reinforcement learning. Instead of linear model quadratic reward, we introduce deep model for both dynamic and reward. And here are several representative algorithm along this family, in this family, where they use kind of similar thing, estimating dynamic and reward, but different thing in the planning part. So I will not dive into the thing, but remember all this planning part has very strong drawback, which is the dynamic and the reward are now nonlinear. If you're familiar with control community, basically before our work, I don't know any algorithm which saying if you give me arbitrary nonlinear model, I can still achieve the I can still provide a practical algorithm achieve provable optimality solution for the planning part. Meanwhile, also the exploration part now become difficult. I think with this kind of introduction, we seems like notice something which is largely ignored in the RL community, which is there are a trade-off, which is between the modeling part, exploration, and planning. As I mentioned, if we use very complicated model, very complex flexible model, we're good at the we have very small modeling error, but it becomes very difficult for us to do the exploration and the planning. Vice versa, if I have simple model, the planning part and the exploration part becomes easy, but the modeling part becomes very difficult. Far away from the practical setting. So basically, you didn't get a readable solution. So that's give us a very nature questions, which is, do we have a practical algorithm with rigorous theoretical guarantee to achieve balance between these three factors: modeling, exploration, and planning? The answer is yes. Otherwise, I would not talk about this today here. So we propose representation-based reinforcement learning to explore model-based reinforcement, model-based information to provide reasonable linear function space for model-free planning and exploration. So basically, by this thing, we will achieve some more balance between modeling, exploration, and planning. So this is the whole motivation and our solution for the problem. Any questions so far? Okay, if we don't have questions, and let's start with how we realize that kind of thing can solve can achieve balance between the trade-offs. We first start from very yeah. So I noticed somebody asked, can you, what do you mean by? Oh, modeling. Okay. Here modeling has different meaning. Like in model-based reinforcement learning, I mean modeling is the dynamic model, but in model-free reinforcement learning, we mean the Q function or the policy function modeling part. Okay, is this answer your questions? Okay, so come back to how we realize such kind of representation-based reinforcement learning. We first not go to learning part. We just consider the planning because we notice the major difficulty actually came from we don't have a way to solve the nonlinear control. So we go back to the stochastic nonlinear control. Okay, I shouldn't say use model-based reinforcement here. I should use exactly this term, model predictive control. So at this problem, it is a very classic stochastic nonlinear control problem, where you have F as dynamic and epsilon as Gaussian. F can be arbitrary nonlinear, so we don't have any constraint yet for that. Meanwhile, we have reward function. So reward function is also a non-convex optimization, non-convex function here yet. Okay, if you utilize if you just consider it as an optimization problem, it's optimization super difficult. I don't think anyone can utilize existing toolbox or existing method to solve this one without any assumption. Okay. So we were stuck here for a while, and then we realized, okay, what if I don't formulate the stochastic nonlinear control in this way? We rewrite the dynamic in another way based on its conditional transition operator, which is I wrote here T. Essentially, this transition operator is equivalent to this. I just rewrite it into the distribution perspective. Okay. And after that, I realized, okay, we can factorize this transition operator without any computation effort because we know the closed form for the Gaussian SVD. Okay, so we can have two ways to factorize it. One is, I think, if you guys know kernel, Gaussian kernel is reproduce kernel. We can factorize it in a corresponding RK-chat space. So this is a Gaussian kernel, and this is Gaussian kernel. Meanwhile, we can also use random Fourier feature, or in other way, Fourier decomposition. Sorry, Fourier decomposition to factorize this. I get the feature here and the feature. This is sine cosine feature. This is also sine cosine feature with the inner product over the Gaussian mirror. Okay, so far so good. I think this is important. I will use this later. But before that, let me make sure we understand this. Yeah. Okay. Because I should good questions. Here, I just want to formulate it into a control part. Control, you usually don't have reward, they have the cost. So here R as cost. Okay, sorry for the confusion. But anyway, if I switch the cost to negative, so basically that become reward, so it become max. Is this answer your questions? And nothing special. Okay, so far we clear about this. Actually, this is basic. I mean, this is basis of whole representation reinforcement stuff I proposed here. Okay, if you understand this, actually it becomes build a connection between the stochastic nonlinear control to the linear MDP. So in linear MDP, we have a transition operator can be factorized in this formulation, and reward is here. Even we don't have such kind of assumption, we can just concatenate the reward into the original R, and we will have such kind of stuff. So usually we don't have this kind of constraint. We just concatenate the phi with art. So we have both conditions satisfied. And then let's look at a very important property here. We can rewrite the Q function with linear formulation over phi. Actually, it's also very simple. Recall this is the Bellman equation, right? For phi function, sorry, for Q function. And then we plug the factorization into T, and we split a little bit, we obtain this Q function equal to phi transpose theta plus this integration. And look at this integration, basically it is constant because I integrate all the variable stuff. So, which means if I can factorize the transition operator, which we can for the stochastic nonlinear control without any computation effort, we can find the space phi such that Q function lies linearly in the space. Okay, I think if we understand this, okay, before we dive into the algorithm, let me answer some questions I always met during the rebuttal when I submit the paper. People always think this linear or low rank MDP is a special model, but I don't think in that way. Actually, I would say it's a very generic structure because for arbitrary transition operator, we can always factorize it. The only difference is how large the rank is. Okay, how large the rank is. But remember this, for larger rank, theoretically, we may don't have an efficient way to solve it. So I think that's why we focus on this linear MDP structure with low rank. Although low, actually, it's not that low. But it's also generic enough to major problem in practice. And also this kind of structure have been discussed since 2014 and later rediscovered in 2020 and so on and so forth. But they always assume this kind of stuff. But I think we should keep in mind that this is not assumed. For arbitrary operator, we always factorize it. The only difference is how large the rank is. Okay. Yeah, and then come back. I think based on the observations saying for the stochastic for a given transition operator and given reward function, we can extract the structure. We can extract the linear representation based on the F. And then we can do the backup or TD update in the obtained representation linearly. I think that will solve the difficulty, or that provide a solution for the stochastic nonlinear control with provable guarantee and practical algorithm. So far, so good. Any questions about the algorithm, about how we construct the feature and so on and so forth for arbitrary stochastic nonlinear control? Okay, and if we don't have questions, I think at least the first thing we should keep in mind, by this representation perspective, we solve a notches problem in control community. If you give me F, I can do planning or in a practical way, but with probable guarantee. Okay, so we have a balance between flexibility and planning guarantee. And the only thing left is actually exploration. Okay, but don't worry. Actually, we can utilize the Thompson sampling to balance the exploration and exploitation, where we maintain a distribution of the. Oh, sorry. There's a question said, what kind of overfitting problem did you see because of kernelization? I don't get the questions. Can you specify the questions a little bit? Hans? Yeah, maybe you can just talk me. You don't need to type here.
Can you hear me?
Yeah, I can.
Okay. So I'm assuming there will be some overfitting problems with respect to the fact that you use the kernel, right?
Let me go back to here. I don't have any learning. Okay. Here is control. The point here is that look at here. I just treat it as a kernel, but everything inside actually is known because this is a control problem. Okay, control means you have model. You just want to find the optimal policy from it. So basically, f is given, sigma is given, and I obtain the factorization by kernel by reproduce kernel property or the random feature property. So there's no learning here. So I don't think there's overfitting problem here. Is that
Thank
what?
you.
Yeah. And the learning only shows up in where in here the blue line, but blue line is actually doing a least square regression given the provided feature. So there's no overfitting. Yeah. Rahul, what's the meaning of planning question mark? Yeah, it is just planning. Or sometimes, in reinforcement learning and in control community, we have different kind of terminology, but I use them interchangeably. For example, I said control and planning here are always saying, I give you a model, you just give me the optimal policy. And this is kind of, I call it control or planning. Yeah, learning will be a different kind of problem. Okay, So far so good. And then we utilize the Thompson sampling to do the exploitation trade-off. The idea is also simple. This is also existing results, which I maintain a distribution of the dynamic. And then when I do the update, I'm updating the posterior of the dynamic. And every time I sample one from the distribution and then do the planning, utilize the representation, utilize the method I used here in the linear space to do the planning stuff. Okay, I think that's our first idea. And because of this good property of planning in the linear space, and also good property of Thompson sampling, actually we can obtain the regret. Also, this kind of result is not difficult to obtain. It just follow the, okay, it just follow, I forgot to list the reference here. It just follow the Ian Brand and also Ben Van Rijd's Bayesian posterior Thompson sampling results and obtain this kind of regret bound. Regret bound means the how far after you see k episode the solution obtained compared to the optimal policy there in terms of the value function. Okay. As we can see, we can guarantee this. I think this is the one which first characterized the regret for arbitrary deep in model for dynamic and reward. And then next, actually, it's the most important thing we care about, which is the empirical performance of the whole method. We compare, because this is the kind of model-based reinforcement learning, just utilize representation for planning. So we compare to the model-based reinforcement learning here, including the several, for example, here. These are different kind of algorithm utilize random shooting and TRPO and the CEM to do the planning part. And speedy is our algorithm. DPSF is deep successor feature because we call ourselves as a representation reinforcement learning. So among all this thing and all this 10 module code, we actually achieve the best ultimate performance. But actually, I hide a little bit here because I hide the comparison because to the policy, to the model-free reinforcement learning. I thought before we do the experiment I thought this will be better, but actually it's not. Unless I change the model instead of fix the F and instead of fit F first and then do the planning at 2 stage. I just use the model-based fitting as a regularizor and then do the planning plus with the planning part, and that will achieve better performance. But this is different. It's not aligned with my theory. But anyway, I find a way to achieve comparable performance or sometimes better to the model-free parts. But anyway, notice somebody raised hands trying to ask questions. Yeah, who is that?
Yeah, it's me.
Mhm.
Something. Okay. Thanks for Professor Dai's great introduction. I have a question. So I heard you said you use linear representation. So I want to ask, is linear representation is enough for some complex task? Can we use some non-linear representation?
Yeah, we will talk about that later. We will talk about later. And this is only the how our idea generated. Okay, please.
Okay. Great.
We will achieve there. Yeah. Anyway, so this is our performance, and then we at least we paused here. We can think a little bit about what we have and what we have not achieved. First of all, it's like I think the most important message is like linearization. Actually, it's very promising to achieve a probable control algorithm for nonlinear control, which bridge model-free and model-based. But we notice there are gaps between the theory and the practice. I think look back into the algorithm where there are three major reasons. potentially. One is like we use kernel or random feature are all infinite dimension, while in practice we truncate it. So I think that's one potential error. And second is that in the Thompson sampling, we need to maintain posterior, which in practice we utilize the ensemble stuff to maintain the distribution, which also introduce approximation. Third one, this algorithm is applicable for Gaussian noise, which we assume. So I think that might be the error which vary the method to achieve better performance. And so then the natural question is, can we do better? Can we avoid such kind of limitation? Yes, we can. Actually, look at the algorithm. We don't need F divergent, F dynamic. We only need the representation. So why not directly fitting the representation directly? Instead of fitting a model and then get a representation, how about we directly fit the representation? I think that's what we want to do. But actually, that's not easy. Because if we directly list the MLE here, look at this one. Okay. You see, it is including a constraint, which is including not one constraint, including infinite many constraint, which is not easy to do. Even just for one, it includes integration over S prime. It's also not easy. It's intractable basically. Another one is, can we avoid the Thompson sampling to maintain the posterior, but just use UCB, because we know the UCB for the linear representation is easy to calculate. But that's also not easy because the feature is blurred. It's always changing. Okay, I think next we will look at how we deal with this kind of stuff, especially how we can find an alternative for solving this representation directly. Okay. This is one idea, but it failed. So instead of directly fitting a constraint, we can introduce normalized condition distribution. So I think it's very nature to exploit the idea from the entry-based model, which people have investigated for almost 2 decades. So, but that's not applicable here, because if we just introduce this kind of partition function Z, our Q function will be relies on the phi over Z. That's not easy. Okay, that's basically saying your Q function require a partition function calculation. That's not good. Okay, and we try another one. Actually, it's very rare nature. Besides MLE, how about we try the contrastive loss? It works actually. We introduce the ranking-based contrastive loss, which leads to this object function. Here, let's look at this one. This term is like the positive sample, if you know that, from the data. And this one actually it came from a negative sample we want to learn. Okay. And we can show this kind of object function leads to the solution looks like this, where P as prime is the negative sample distribution. But don't worry, we never utilize this part. We only need to find, so it's fine. Okay. Any questions so far? Any questions so far? Okay, if we don't, yeah, this is one alternative. We notice there is another alternative. Because we already noticed, okay, we can utilize this kind of factorization, introduce P here. Potentially, is it better we start from here instead of from original one? The answer is yes, because with this, actually, we can with this factorization, actually, we can have an equivalent formulation. Look at from here. It is also easy to obtain by introduce PSA on both right-hand side, left-hand side, and divide that by square root of both these two things. We obtain this part. And after we get this, okay, we can use the L2 to direct compare left-hand side, right-hand side by this. And by some very easy square expansion, we obtain equivalent object function like here. Okay. So for each term, it is compatible with stochastic gradient descent. So we can directly use stochastic gradient descent to minimize this object function, which is corresponding to this two term. So yeah, this is a second way we can do the factorization directly. Okay. And the third way actually is also very interesting. Instead of viewing it as the SVD or decomposition stuff, we consider the latent variable model. We rewrite the latent variable model into the inner product formulation based on L2. And then it's obviously we can consider the phi SA, the PZ given SA as my phi function, and P S prime given Z as my mu function. Okay. And then we have my Q function will be looking like this formulation. Okay. And besides that, the benefits of consider the phi and mu at both distributions is that we can utilize the elbow, which is widely applied in I think almost every people working on machine learning should know this kind of stuff. We just do the elbow and treat it as a latent variable model to fit the phi and the mu. And then we can get an algorithm framework. So it's like model-based reinforcement learning, but different kind of as model-based reinforcement learning will fit dynamic. Here we fit linear representation by either contrastive loss or SVD or elbow and so on and so forth, just to get the phi function. And then we can calculate UCB for exploration part. Finally, we based on the representation to execute as Bellman equation to do policy evaluation and then do policy gradient, so on and so forth. And then we use that to collect data and so on and so forth. This is the whole algorithm framework. Only difference like how we learn the representation. Okay. And we can achieve the sample complexity with such kind of sample complexity. We get to the epsilon optimum policy. I will omit the proof here, but I think this is important to say, okay, the algorithm itself can, even you don't learn the model, just learn the representation, it's also good enough for you. So far, so good? Okay.
Okay, I have a question regarding the algorithm. So it's if we use the linear representation, is accurate enough to model the agent dynamics or model the agent to word model like that. So we can use this to model everything. And how about the sample complexity if we use this?
I didn't get the question. Can you repeat it?
Okay, I want to say, if we use this to linear model, right? Use like a linear representation to learning the model, and then based on the model, we can use this to planning, right? So I want to know how accurate the model is.
Well, that's a good question, actually. We have okay. I will postpone the answer to the question, and you will see how accurate it is. Okay.
Okay. And another question is, based on we learned the model, yeah. How about the sample complexity? Yeah. So if we learn the model, what is the sample complexity? If we don't learn the model, what is the sample complexity? So can we compare the two settings and say what we improved regarding sample complexity, like sample efficiency?
I don't know what if we don't treat it the model-based reinforcement to prove it. The major problem is that I don't know existing results saying I can directly fit the Q function with arbitrary nonlinear model with tractable algorithm to obtain the exploration part. I think that's a major bottleneck. I don't have any idea whether that's such kind of bound there.
Okay, gotcha. Okay. Yeah, thanks.
And then now I can safely put everything in my table now. Okay, you see, I have model-free reinforcement learning, the model-based reinforcement learning, and also have my speeder here. Basically, achieve almost the state of art of the performance among all the environments. Even sometimes it's not the best, but it's, look at here, it's just comparable. Okay. And this is ultimate performance. And then look at here, this is like the, how fast it converges. And I forgot to mention all this kind of experiments, including here, follow the benchmark of the model-based reinforcement learning in that paper. We follow their protocol for with their same environment to keep everything fair enough for every algorithm. Okay. Yeah, here's the blue line is our algorithm. We can see that the algorithm indeed achieve convergence faster. Okay. Yeah. And then here's the summarization. For this moment, we can safely say we provide a strategy to avoid the previous mentioned error and generalize this kind of linear representation stuff for efficient exploration, efficient planning. But there's still a problem, which is, as Shanning mentioned, how this algorithm can be applied for the practical setting, where observation is not state, but the observation is like image, video, text, and so on and so forth. Yeah, that's what we will explain next. But before that, actually, I want to emphasize a little bit thing here, which is we all talk about online setting, but actually the algorithm can be also utilized offline data easily. Even the offline data you obtained is not from expert, not from the perfect policy, but no worry, as long as it is such kind of transition operator, the data from the same transition operator, we can use that to train my representation. Okay. Actually, we did some experiment on that, but I didn't include here. Okay, I think then we will answer the questions I mentioned here. How good this our method if we apply it to practical. As we mentioned, practical we have rich observation, but maybe not sufficient enough. Even it is rich, it's not reveal the whole sufficient state from the single image in the whole sequence of the video. Okay. So we have no choice but utilize this kind of POMDP. It's almost the same as MDP, but one more thing introduced, which is the because we didn't observe the whole state, we can only have the observation. So we introduce emission distribution, which is saying given current state, it will emit observation from the state, introduce the image observation from the state. And here is some known result talking about how difficult the problem is. It is difficult in terms of both computation and the statistics, in the sense that in terms of the computation, even I give you everything of the POMDP, like omission distribution and transition distribution, and I ask you to extract the optimal policy, it is still p-space complete, which is even harder than P. Okay. And for the learning part, if I ignore the planning, it is still also difficult because the sample complexity now is exponential with respect to the horizon, which is called curse of horizon. So it seems like this problem is difficult, but no worry. If we consider some structure in the problem, we can obtain this efficient sample complexity. But still, even we have some efficient sample complexity, we don't have efficient way to solve it. It just say, assume you have a planning oracle which can solve the planning part. You can solve the learning part with not with sample size, not exponential with the horizon. Let's look at why we think the planning in POMDP is difficult. Because we can introduce a belief MDP into it. But the major problem is that the belief now becomes you need to utilize the posterior, Bayesian rule to calculate the posterior, first of all. A second, belief itself is a distribution. And the distribution itself is not easy to model, I would say. And not even mention you need to calculate the TD update or Bellman backup upon the belief. So that's even difficult than that. And then we consider a very special structure called L-decodable POMDP, which is saying it's not relies on the whole history. It's only relies on a past L window size history. So this will really, previously people only think this will reduce the sample complexity of the POMDP learning, but actually we argue it's also introduced some useful information to provide the efficient planning algorithm for that. Due to the time limits, okay, anyway, I will explain why it's not easy to first directly apply linear representation here, and then we will consider the way to utilize L-decodable to obtain the linear representation. The major difficulty of utilizing linear representation for POMDP is that instead of, we definitely can write the Bellman equation like this, but the major difficulty is that the integration only take care of last part. Okay, you still have something overlap with your XH, which means the previous factorization for this is not enough to give you a linear representation. I think that's equivalent way to explain why the POMDP planning will be difficult. I will skip here. Basically, after we expand based on the L-step decodable assumption, we utilize the multiple step Bellman equation first, and then we break the dependency between here and here, and then we utilize the L-step decodable assumption to prove there exists a factorization to factorize this to here. So it doesn't depend on then it will obtain the linear representation. I will omit the detail here, but remember, after this model step looking forward and L-decodable assumption, we can obtain the linear representation for that, for the model step Bellman update. I think this gives us saying, okay, with this kind of thing, we can have second term linear representable by some representation. And similarly, for the first term, it's also linear representable. So eventually we can say, okay, my Q function can be linear representable as this. So the rest will be the same as I used in the latent variable representation for the MDP. Okay, here is the way I compare with current state of the art method for the POMDP setting. And I also list the best MDP setting here to demonstrate, okay, this L-step decodable is not that bad. Okay, and first of all, we will compare to the state of art the POMDP algorithm. We almost achieved the state of art performance among all the environments here. And compared to the best of the full observable MDP setting, we say, okay, for example, look at the cheetah row. The L-step decodable assumption is not that bad. Okay. Okay, here I eventually apply this to the image or video-based stuff. The architectures look as I have the video and I have future video, and then I have the encoder decoder part extract this from image, and then I have transformer to capture this operator here, and then MLP to predict the latent stuff and go through decoder to the image, so on and so forth. This is like I compare to all the meta word task. The blue bar actually is our algorithm. The green bar actually is the Dreamer V2. I think here we can see the algorithm performance. Some tasks perform comparable, but most of the tasks achieve better performance compared to the Dreamer V2. Also similar here is like I just list a part of the conversion speed for that. Shangling, sorry, I forgot to include some prediction figure here, but actually in our paper we listed some figure to show how good the fitted model is. Okay.
Okay, no
I
problem.
think this answer your questions. I remember I
Yeah.
thought I did that, but it seems like not.
Okay.
Uh-huh.
No problem. Okay.
Uh-huh.
Mm.
Yeah. Okay, I think this is the whole content of the talk. And lastly, I would like to echo some relationship between what we proposed to, for example, something called Alberta Plan Enriched Studies paper and also Ian LeQuin's proposed white paper. Essentially, we almost share the same philosophy, but I do believe we should utilize representation more instead of just feeding representation. Sorry, instead of just feeding the word model and the policy separately. Okay, I believe representation will become a bridge to bridge all this separate, for example, model transition model, policy, and value function, and similar here. Representation will become a bridge to the word model, to actor and critic, so on and so forth. Okay, I think here is the paper I mentioned during the talk. As I mentioned, this is a long-term project. We work on this since the end of almost 2021. It's already 3 years. This is the paper we discussed today. And I'm still working on this direction, and here are something more beyond the talk I provide here. I think one thing I should mention is that this paper, diffusion and spectral repetition. As I mentioned, I utilized the contrastive loss, spectral decomposition, and the latent variable elbow fitting to get the repetition. But actually, recently we find we can use diffusion model to extract the feature. It is both give me better generative quality, and also compared to the diffusion model based reinforcement learning, we don't need to do the diffusion in the inference stage because I only need the representation, so it is more efficient in terms of the computation or inference computation cost. Okay, another part, actually, that's why it's like we utilize the representation learning for the sim to real. It's also achieve better performance in real application like the drone control. Here is the code base. We released the code for the paper I just mentioned, including the new paper like here. And yeah, that's all. And any questions so far?
Okay, there is one question from the audience. Could you also share the slides? Okay.
I
Go
think
ahead.
you mentioned in the beginning, this is a recorded session. I'm not sure if Professor Diden allows to upload this on YouTube. If this happens, the slides will be part of the video that we upload there.
Yeah.
So you can find this maybe later on YouTube.
Okay. Yeah, I have a question. Yeah. So the experiment results is very good, is very impressive, especially compared to German V2. Yeah, at the end of German V2 is currently sort of baseline. So, do you think is this our future direction for efficient learning? We use the word model, or you use learning representation.
I didn't get questions. Shani, can you repeat the questions?
So
Okay.
I want to ask, is learning representation features is a future direction to the efficient learning? So
I don't know. I believe so, but otherwise I will not work on this direction. Actually, we currently trying to utilize this kind of view to see whether we can contribute to the large language model stuff we
Yeah,
have some
yeah,
progress. I
yeah,
think if we have some good result, then I will be more confident to say something about that. But at this moment, it's only from my own opinion. I believe that it's
yeah,
very good.
yeah.
Very, I would say, at least a promising direction to
Yeah,
work
yeah,
on.
I think it's a very
Uh,
promising. Yeah.
uh,
Uh,
Okay.
a question maybe you mentioned in the unsim to real transfer approaches that this might be suitable for. So do you think they inherently, there is the reality gap problem, right? Like the difference between the simulation and the real system, and then you're learning the representations in the simulation, right? Do you think the reality gap will be a problem and how you can actually avoid it in the
yeah, actually, look at here. Can you see what I'm sharing here?
yes,
Yeah,
skill
yeah, we see here. Yeah, skill transfer. Yes.
Yeah.
Mhm.
The representation actually give you a very easy way to do the sim to real. Look at equation 8, right? I didn't list it in in my slides, but look at equation 8. This P now is some factorization you learned in the simulator. Okay. And the reason you have gap is because there is difference between your real P and P now, right? So we introduce another component which is also linear formulation to learn it. In another way put it, we believe the gap is just because you don't have enough subspace. Okay, so we introduce more. And then the rest is almost the same, right? You have both the feature learned from the simulator and the feature from the real case. And then you can learn, do the reinforcement, Q learning or the other things based on this new representation space. Does this answer your questions?
Yes, yes, thank you.
And actually, yeah, if you're interested, you can look at the code here.
Mhm.
They even have some video stuff.
I'll help.
Yeah,
Oh.
this is like yeah, simulated policy. Okay.
Okay, I think this paper
The
is very familiar. I think I have read it.
Uh-huh.
I'll have a
The
look.
task is like you want to hold in this position and come back. Oh, this is skill. I just utilize our method, but without adding new representation. And this is saying we added more representation and also training practice.
Mhm. Do you know if this was submitted at QRL or
No, actually, this is published on the IROS.
IROS? Okay. This year, right? Okay.
Yeah, this year, yeah.
I'll meet the authors there also. You're also one of the co-authors, I guess.
Yeah. Mhm.
I think I read the paper in the yeah.
I see, I see. Yeah. Okay, sounds good.
Okay, are there any other questions from the audience? If there are no other questions, I think we are done for today. Thank you very much, Professor
Bye-bye.
Dai, for your talk. Bye-bye. And for the rest of you, feel free to join our our mailing list to get the updates for the next upcoming talks, where we'll post the upcoming information. And see you in about a month on the next seminar. Thank you all
See ya.
for joining.
See you.
See you.
Thanks, Shandy,
Bye.
and thanks,
Okay.
Joseph.